The lightning-fast computational power of the Frontier supercomputer has enabled scientists to identify the conditions necessary for producing ultra-hard BC8 diamonds. Frontier, the world's fastest supercomputer, located at the U.S. Department of Energy's Oak Ridge National Laboratory, has helped decode the formation of BC8, an ultra-hard diamond stronger than any material previously known to humanity, according to a report by New Atlas on July 30th. The research team, led by physics professor Ivan Olenik from the University of South Florida, used Frontier to uncover how to create BC8, which is believed to exist only in the cores of massive exoplanets right here on Earth. Their findings were published in the Journal of Physical Chemistry Letters. Diamonds, the hardest known material on Earth, are prized not just for their beauty in jewelry, but for their practical applications, such as in geothermal drilling and as semiconductors in nuclear batteries. BC8, however, promises even greater utility due to its superior hardness. Scientists speculate that this material only forms under the immense heat and pressure found in planets at least twice the size of Earth. Creating BC8 diamonds in a lab is theoretically possible, but it requires simulating extreme conditions. These conditions include pressures 10 million times that of Earth's atmosphere and temperatures approaching those of the Sun's surface. Given the enormity of these challenges, conducting physical experiments to produce BC8 is largely impractical. The Frontier supercomputer can run millions of atomic-scale simulations across millions of different conditions to pinpoint the exact parameters needed to create BC8. Olenik noted that other computers are too slow for such a task. For this study, we needed to simulate over 1 billion atoms while performing up to 1 million time steps in molecular dynamics simulations. We accessed other supercomputers, but none had the computational power to handle this many atoms, Olenik explained. After running the LAMPS software module for about 24 hours on 8,000 of Frontier's more than 9,400 nodes, each node being an individual computer or server, the research team discovered a surprising and unique step in transforming carbon into BC8. Traditional diamonds must first be melted before the carbon solution can reorganize into the super-strong BC8 structure. The carbon bonds that make up diamonds are incredibly strong, so we have to melt the diamond to transition it into the new BC8 crystal phase. This adds another requirement, higher pressure and temperature, 12 million times Earth's atmospheric pressure and approximately 4,700 degrees Celsius, close to the surface temperature of the Sun, Olenik said. Such conditions could be achieved through a series of shock waves. The research team is now beginning to test their newly acquired data by attempting to synthesize BC8 at the National Ignition Facility, NIF, at Lawrence Livermore National Laboratory. The NIF, a nuclear fusion facility the size of a stadium, uses 192 powerful lasers to generate temperatures exceeding 100 million degrees Celsius and pressures above 100 billion atmospheres. Thanks to Frontier, we have a good chance of success. This remains an extraordinary challenge with no guarantees, but we are very confident in the results, Olenik concluded.